Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. So I haven't streamed on this stuff since last Saturday, I think. So it's been a little over a week. And I've actually made a lot of progress in the last week, but on a lot of little things. So I haven't done anything major, like I haven't started on the GPU yet or anything, but I've done a lot of little things. So for the first thing I want to do today is I want to go over a lot of the changes that I've already made now. They're relatively straightforward. It's just that I've done a lot of them and I kind of want to talk about them. I think after last stream, I think that was the one where we were still trying to simplify things and getting the synthesis tools to infer block RAMs for things. So there's a couple things I did since then. By the way, yes, I did set up a little camera over here. It's me pointing at the FPGA. This is the board I've been working with. This is the Max 10 development kit. The camera angle here is not necessarily ideal, but it's kind of the best thing I can do in terms of being able to reach over and press the reset button without screwing everything up. And at least you can see the LEDs. I try to get those in focus. There's only 3 of them that I'm actually using. Counting from the nearest to the camera, there's 0 I'm not using, 1 I'm using, 2 I'm not using, 3 and 4 I'm using. And this is just a down counter. This is actually happening from C code. This code does a couple things when it runs. I'll actually show you. I'm just going to pull up PuTTY here. Connect to COM5 with a 9600 baud UART. Slow as shit, but it'll work. And then I'll reset this. And you'll see it printed some stuff over to my UART. Or over to my computer via UART. And then started blinking the LEDs. And this just says we're in main, and then just some long message because I needed to test longer strings. And then setting the initial LED value, and then it goes into the main loop. And that's the last thing it prints. So that's pretty cool. Can actually show you guys this code too. This is the entire ROM here. I guess let me bump up the font size before I forget. So we got some type defs. We have some register definitions. I'll talk a bit more about these in a minute because these really gave me a headache this weekend. And then I have a simple put char implementation here. And it just checks the UART transmission status to make sure that it's not busy. And whenever it's not busy, then it'll go ahead and just output this character to this write register. And then that will start the transfer. And then I did a put s as well, which takes, a string just as a constant char pointer. And all this does is just sit here and puts out characters, and then at the very end of it, it puts out character return in new line. I think the C standard library puts put s. I think it only does new line, but this is because at least when using PuTTY, we need the extra character return, which is fine. I mean, the fact that there's this XW prefix on these means really I can do whatever I want in here. So. It's up to me to make those decisions, and that's what I've chosen. I've also implemented this XW cycles, which will give you the cycles since the processor started running. And this is actually implemented in assembler. The assembler stuff I'll get to in a second. And then the main is really simple. There's a put s to put out this string, another one to put out this. Then I set up this LEDs variable. In fact, this actually only sets up the variable, but yeah, doesn't matter. And then it says main loop time, and then in the main loop, we output this LEDs variable output to the actual LEDs register, and then just decrement the variable, and then wait a bunch of time. I calculated this to be, this is what, 2 million cycles, 20 million cycles, and I think that's about 0.13 seconds, which is what it looks. That looks about right. Looking at the blinking LEDs, that's about how often that value should change. So that's as far as I've gotten. So basically I implemented UART transmission and the LEDs and also Bootstrap C. Before I move on while I'm still talking about this, I should show this assembler code as well. But it's actually really simple. There's the entry point, which is just a jump to the stub thing, which just is in the text section. I'll talk about the linker stuff here later, but it just copies the data sections because our program is going to have, like code and then data sections, and the data sections need to live in ROM in order for the program to know about them, but then we have to move them into RAM. So this does that relocation, and then the same thing with well, almost the same thing with BSS. BSS is uninitialized memory, but we make sure to clear that to zeros anyway. So there's that. Then we set up the registers, and these all just come from the linker script. And then we jump into main. In fact, we call it, and then we'll jump to the stub in case main returns. It shouldn't do that. But in case it does, that solves that problem. And then here's the implementation of that XW cycles thing. And I put it into its own text section. That just makes it easier to see when I'm looking at this assembly, which I'm doing a lot. And the fact that I prefix it with .text just means that it gets treated like any other text section, but it's in its own section here. And then all it does is just reads these cycle counters, which are internal CPU registers. It reads the high one twice in order to make sure that this hasn't basically overflowed, because you can't really do an atomic 64-bit write with this 32-bit CPU. So that's just how this works. And this is actually recommended by the risc-v manual. You'll notice I also use a lot of I don't do it like here because we have these high and low macros, and that's because these have to be filled in by the linker later. So I will write these out like the proper instructions here. But in a lot of cases, I'll use like ret. Like a lot of these, or even these RD cycle things are pseudo instructions, and I just use those whenever I can because they're easier to read. I feel better about them because then I feel like I screw up less when I write them. But it's that easy. That's all the code there is. So it's just some simple bootstrapping and then the C code, and there's not even any headers right now. It's just all in this one file. And it generally works if I have optimizations turned on. If I turn them off, some weird stuff happens, and I haven't quite finished debugging those yet. To be honest, my whole debugging flow is really crap. I'm basically just adding things to signal tap and also just looking at dumps of the actual logic over time and just like finding things that are weird. Like I'll know based on what it put over the UART or what it's putting on the LEDs, kind of where it went wrong, and then I just start like removing delays and stuff and looking at these, and it's a really painful process. But it is going forward. Like I am fixing a lot of small bugs, so it's not all there yet, but there's enough there that at least things seem to be looking normal for the most part. I thought about debugging some of this stuff on stream, but honestly, I just don't want to right now. So I spent a lot of time this weekend doing that. So I thought we'd do something a little more fun. But I'll get to that. I want to talk a little bit more about getting to this point first. So since last weekend, the first thing I did, I think we finished by working on the register file, and I think we were trying to get it to infer blockrams on the registers. I want to actually take up the netlist viewer here so we can look at some of that stuff. Because I was able to simplify it a little more even and get something that's actually kind of cool. So again, here's our top level stuff. We'll go into the Xeno wing. It's so cool to watch this thing come together over time. I'm really enjoying this. But in here, there's a couple new things, like here's the UART transmitter. In fact, this is actually the interface to the UART transmitter that the memory mapper talks to. There's the memory mapper, so I think our CPU's over here. Yeah, there's our actual transmitter. Wait, what was I going to look at? Register file. That was what I was going to look at. And then we need the CPU. The CPU I also split up into separate modules now. And we'll get to why I did that and why I'm not terribly happy with that decision right now. But because I think it's actually a source of a lot of the bugs. But we'll worry about that in a second. So we look at the core, which is basically where the actual CPU logic went. And this doesn't look too much different than last time. Probably messier than what I had on stream, but it is actually less logic elements. It just looks crazy because of the layout. And in here, I think the register file's here. Go ahead and go in there. So I did end up getting this to infer a RAM. I think I did that on the last stream. And this generally works really well. The logic here is really simple. I think after the stream, though, I think I ended with something where it did do this memory. I know a lot of this is out of the, or I know like my overlays and stuff are in the way of this, but it really doesn't matter. You're not missing anything on the right side of this. It's basically just the RAM tied to the outputs. Anyway, I think that when I left that, this was a little bit simpler because it didn't actually ensure that register 0 was 0 all the time. So what I ended up adding was a tiny bit of logic. I'll pull up the RTL for this. Where's my register file? Here. So I did a couple things here. The first one is this. When it's writing, it just won't write when the register adder is 0. So that's trivial, obviously. Maybe I did that on stream. Anyway, I had actually went through a couple iterations of this. The first one I did is I took the regs here and I made it go from 1 to 31 instead of 0. And the reason why is because that way I would only store, the upper 31 and not actually store R0. And then I had some logic for when it was going to read it that did some conditionals on the address. So if the address was 0, it was going to be 0. Otherwise, it was going to read from the array. And that was okay, but it actually turned out to be a little bit better because I'd also had to put muxes on the outputs of the RAM in case it was 0. So the simpler one was to just realize, well, we're just using an FPGA anyway, so it's okay that we just use these initial blocks. So this will actually specify what the initial value for these registers will be on startup, and as you can see, I just clear all of them because why not? And then, so as long as they start at 0 and then we're never able to write over the register 0, then that is fine. And then we can remove the conditionals here, and everything gets really simple. And that's what allows us to have just a tiny bit of logic here so that it never writes the first one. And then the output is trivial. So this became a lot simpler when I did that. So that was one of the first changes I did. I did a lot of these changes just last weekend, and it was kind of refreshing to not do them on stream because a lot of them just took a lot of iteration for me. But anyway, it did work out pretty well. So that was the first thing I did. The next thing I did is I'll talk about these CPU changes. So I split up the CPU into different units. The CPU as it was became the core, or what I call the core. And then there's a couple muxes and stuff here. But the other major units that I separated out here, I separated out the store, what I call the store unit, and what I call the load unit. So I greatly simplified the loads and stores. Let me pull up one of these units on their own, just to show you what that kind of looks like. We'll show it here too. I think they're not that pretty actually in the RTL, but they're not terrible either. And the whole idea here, let me see if I can just move this. Nice. The whole idea here really is just that these have their own interface to the core and then to the memory themselves, and they handle like all the misaligned stuff. So this is the load unit, and so when a read request goes to this, then this will issue it to the memory rather than the core issuing to the memory, and it knows that it may only have to read one of these or do 2 loads here, and that's it. So that ends up being a lot simpler. And the logic itself is a lot simpler because I did a lot of this stuff as shifts, rather than I basically load the word that it's going to read. I basically read in a whole 64-bit word, and then if I have to, and then I do some shifts to figure out which of the bits we actually need from there. So it ends up being a lot simpler. The downside, of course, I'll show the store unit too here. And here again, whenever you do a write, it actually pulls the data that you want to write into a word, a 64-bit word. So it'll shift it based on the address and then figure out the byte enables also with that. And then it will go ahead and either write 1 or 2 bytes here. Or sorry, 2 32-bit words here. And again, it'll figure that out by itself. Now, the downside of this approach, so the upside is that all this becomes separate from the CPU. So if we look at how it's used in the core, then the loads and stores become really simple because they basically just dispatch. So this load state dispatches to the load unit and then just waits for it to finish. The store one, I think, just dispatches, and then the write back stage will wait for it to finish if it has to, or at least finish asserting that state. So it's pretty simple there. The downside, though, is that the CPU part itself suddenly basically has 3 separate units that it has to arbitrate for the actual memory bus. And that logic is not terrible, but I think it's the source of some errors right now. So I'm not entirely happy with that solution, just because, again, while it makes the units simpler, we are actually starting to get some out of order stuff because these basically happen asynchronously. And it's a bit of a shame because I was hoping to kind of avoid all these kind of issues by not having a pipeline CPU, but then by separating out these units and introducing some of that async behavior, we kind of run into a lot of the same issues. The way I've just sort of solved it so far is I just have the load and the store units take precedence over the core unit here, which is really just the instruction fetch unit, which I haven't separated out from the CPU out of laziness. But yeah, I've actually seen cases where, for example, the store unit will store 1 byte, and then on the next cycle, the core ends up starting to read instructions, and this causes some issues. So there's some things I have to debug in there. But other than that, that's sort of the main change that I made there. What else did I do? I just did that in 2 steps. I first separated the load and store units, and then I separated out the core unit just because it made this stuff separable from the core logic, which was really nice. Couple refactorings after that. Sir Black, thanks for the follow. Yeah, what else did I do? Yeah, so then the other thing I did is I hooked up everything to the DDR3 memory. So that was not terribly difficult, actually. I realized today that I made some really dumb mistakes in the implementation, but I seem to have fixed those. And I figured that because I'm not really doing a lot of like unit tests for this, so what do you expect? So let me show you the updated memory map. This will also include some other stuff, but there's some cool things here. So if we go into our docs, by the way, all this stuff I'm just doing like piecewise, so it seems like a lot of work, but I've been working on this maybe an hour or 2 every night, if that. So it's been all kind of baby steps, but it's all kind of coming together a lot in the last week. So let's see. So yeah, so I had a couple notes that registers are marked RW or RW, depending on the usage, and then reads or writes, if those aren't marked as such, are undefined. And that just allows me to make some decisions that are actually kind of nice. Like the UART, for example, is really only 2 registers, a read one and a write one. So I actually make the reads always return just the value of the read one, and then the writes, they only work on the proper write one, but otherwise they do nothing. That's kind of neat, but... Anyway, so I have the program ROM, the system regs, and the DDR3 memory. Maybe I already planned out where this was going to be in the memory map, but anyway. This, I also have a mirror here because it only takes up half this address range, so I did that. And then, yeah, I've elaborated here where the system registers are going to go. And so I decided that the different sets of system registers are going to be, I'm going to use these 4 bits to decide where they are. So this first one is the LED interface. The second one here is the UART transmitter. And then that allows me to have 14 more of those, even though right now they're all mirrors. So I figure that's going to be enough. If not, I can move stuff around in the address space. It doesn't matter because I own the hardware. Anyway, so I did that. Hooking that up ended up being... I kind of am really happy with how simple this ended up being. There was a couple more lines to the memory mapping logic, but then the interface itself is actually really basic. This is the whole thing. And the main logic here, hold on, let me see if I can zoom out there. This is the entire thing, where there's the memory interface on the right, basically, and then the interface to the rest of the system and the memory mapper on the left. Now, the whole logic for this ended up being pretty basic. It ended up being able to just route a lot of the stuff just straight through this interface. One of the things I kind of have to be careful of, though, is because we have the memory mapper has a 32-bit word interface, but then the DDR interface is a 64-bit word interface, and so we have to map. Like we know that the memory mapper is always going to give us 32-bit aligns, like reads or writes. But then we need to align those to 64 bits, and then we also need to just basically decide if that's the high word or the low word of those 64 bits that's going to write to. And so we take this bit 2 of the address and we stick that in a FIFO. So whenever we get a read, we read that part of the address into the FIFO, and then whenever the underlying memory interface gives us a word back, then we pull that address bit off of the FIFO, off the other end of it, and then decide whether or not we need to shift the data that came back from that when giving it back to the memory mapper. So it ends up being kind of simple, and some of the logic here is really basic. But But I was kind of happy with how simple that became. So that was actually pretty nice. Let's see. Oh yeah, another thing I did is I changed the memory mapper so that it's actually possible to read outside of the memory map, and the CPU won't just hang. Because what would happen before is that, like, if it didn't recognize this address, it would send out, or it would basically ignore the write, and then if it were a read, for example, it would ignore the read, and then, like, the bus is sort of asynchronous. So you put a read command on the bus, and then eventually on the other half of the bus you'll get some data back. What would happen is you would issue the write, and then the data would just never come back. Nothing would respond to that. So what I did is I added this dummy response thing here. So if it couldn't recognize the address, it just goes to this dummy read data valid, and then that's just a register here. So if you look at the data valid that comes out of here, where do I set that up? Yeah, here. I just do this. So the read data valid, which is gonna tell the CPU that some data came back, is just gonna fire on the next cycle regardless of what the actual data on that register is. So that's basically reads outside of the memory map are undefined, and that also works fine. But I just did that as sort of a catch-all. I also went through and I did everything. Before I was using asynchronous resets, and now I'm using synchronous resets. The only real difference you'll see, I only have the clock on these edge lists here. Really, the only thing that makes a difference for is it makes it a little clearer to the synthesis tools which one of these is my actual clock. The other thing it does is it allows me to control these from software, which I actually do, because now that we're hooked up to the DDR3, we don't want the CPU to be interacting with the DDR's interface until it's ready. So I actually wire up the initialize done line to the reset of the CPU, and that actually just works fine. That's the kind of thing you may not want to do on a proper chip, but in this case, with how big our timing margins are, this should actually be fine. I also went through in the simulator stuff in the Rust code, and I took the DDR3 test that we did, and I separated out the exact DDR3 simulator parts. So that's its own Rust struct here and its own crate. And that allowed me to, in the Xenowing test thing, I can just pull that in. So I just hooked that up here, and then the other test just kind of works. So yeah, so I hooked all that up. And that was, again, just sort of part of working towards getting the DDR3 hooked up right. When I wrote, by the way, this little FIFO thing that I mentioned here earlier, when I wrote this FIFO, I totally had it wrong first. There were a couple things I did that were really dumb in here that I fixed. And now the code for that is really simple, as you would hopefully expect. It should be really basic. And then there were some other things that I fixed, like in the core, a couple things I had backwards. Like I moved around some code to do some of the instruction decoding. So like one of the things I realized is that up here, I was looking at this function and then always picking the ALU up out of these. And it turns out like there's another bit that can change add to a sub and some other things. But that should actually only happen when you have a register operation. So I moved that down here, and when I moved that, for example, it actually had a bang in front of this initially. So I had it backwards then, so I had to fix that. The initial load upper immediate instruction I had wrong. I don't know if I was thinking about, I think MIPS has an add upper immediate instruction, and probably some other things do as well. For some reason, I thought load upper immediate was that, and so I had it wrong that this would actually do an add, and so I fixed that. Did some misaligned tests, that seemed to be fine. And then, yeah, so then I got C running, and that, again, was fairly straightforward. I had to add this C file here. I need to put a lot of this stuff in like variable definitions and stuff, and use the macros in make to make this a little cleaner, but for now it doesn't really matter. But again, that I showed you guys the assembler code for that earlier, and then the C code, and then there's the linker script is really the only other part. And to write this, I searched around a bunch for a lot of other risc-v link scripts, and also I looked at the other ones that we did for the Virtual Boy stuff. And this is really pretty simple because we have these two regions here. This one is where the ROM is, and I know right now at least it's going to be 64K, and then we have 128 megs of memory at this address. So then most of this is really straightforward. The text section is going to start in ROM, the data stuff is going to be in memory, and then the stack is going to be at the end of memory. So I just put it right at the end -4 so that at its highest value we could still write something there. And that seems to be fine. So the text sections are laid out first. They're just laid out in ROM. First I lay out this entry one just to make sure that that's the first thing that's in here. And then I lay out all the other text sections. And again, this entry thing is just this top code here that just jumps to the first part of this text section. Then I stuff the read-only data in there as well. And then the data stuff is going to be laid out next in the ROM, but it's going to need to be located. So that's what this @ thing does, but it needs to be located, or the compiler needs to refer to it as if it were already in memory. So I just decided this is going to be at the start of memory. There's a couple things here. SData, which is, I guess, small data, I found out. You have this global pointer, and I guess this is pretty common on some RISC systems. If you have a lot of data that is accessed kind of frequently, and the compiler can make some decisions about basically taking a subset of your data sections and saying, okay, this is where there's going to be a very small section that is going to do all addressing in there relative to a given register. This allows you to not have to calculate addresses for everything so much, because a lot of the address can basically just be encoded in the instruction. For something like x86, this doesn't seem to matter much, but for something like a lot of RISC systems, I guess this ends up being a lot faster for certain kinds of data. Anyway, the relative addressing relative to a register in risc-v can only be plus or minus 2K, and so that's why we just say, okay, the data, this global pointer is the SData section, and then plus 2K, and that way it'll give us signed plus 2 or minus 2K for that area. Where we put this doesn't really matter that much, actually, because apparently GCC will actually, as it's stuffing things into that section, it will compare it to whatever the value we provide this for this. So it'll just kind of make it work. There were a couple things here, though, because we need this data start and data end, and these need to refer to where they are in ROM, not in RAM, so that we'll use those things to copy it into RAM. So I had to do some stuff here to make sure that was correct, but other than that, it was easy. And then the BSS stuff is also trivial, and that's actually just designating parts of RAM. This actually doesn't end up doing anything in the ROM, which is why it's no load. And again, those are just uninitialized sections. So that's it. It's super basic. I also enabled some optimizations, and when I disable them, some stuff goes wrong. I'll debug that later. But yeah, another thing I started having to specify the ABI here. So when I was doing all this, by the way, I did a lot of Googling just to make sure I wouldn't mess this up. There were a couple of really nice resources for this. One of them was this. It's called the All Aboard, and I guess it's a series about just looking at the environment in which a lot of risc-v stuff runs in. And a lot of these ABIs and architecture settings here for this GCC are in the official GCC builds. So it talks a lot about which different ABIs are available, different arc options. So that's pretty cool. Extremely helpful. And then there's also, if you just go to the risc-v, they have some of this stuff about this ABI documentation. So I found a lot of the stuff about register conventions and the names of these. And that's what helped me when I wrote that cycles function. It helped me understand which registers I had to output stuff in, which registers I could use as temporaries, that kind of stuff. So that was really nice. Yeah, that was probably the most helpful stuff. And what else did I do? Yeah, so I did that, and then I implemented the UART transmitter. And the UART transmitter, so my board has a UART on it. There's two USB ports over here. I don't know if you can see them from that angle. And I can't remember which is which. I think the one on the right is the UART, and the one on the left is the programmer. Anyway, what that gives me is a virtual COM port on my machine. So again, I can pull up PuTTY and just listen to that. And then whenever I send stuff over via UART protocol, and as long as the COM port on this end agrees with the speed that I'm sending it out at from the FPGA, I get text, or I get data, really. So setting that up was actually pretty straightforward because I had done UART transmission before. So I did a little clock divider here for that, and you can specify the clock frequency and the baud rate, and it'll give you clock edges. And then the transmitter itself is here. There's a few states: idle, start bit, and stop bit. I should actually pull up the documentation on how UART works. This, by the way, is just some Arduino communications protocols tutorial. It seemed kind of cool. I'll actually put this link in the chat. And UART is a really simple protocol. You basically have the bit rate here, which is the timing between different parts of this protocol. That's already like predetermined. Your transmitter and your receiver just have to agree on that. In this case, I'm just using 9600 baud, which is like baseline. It's total crap. I should actually be able to raise that because I think the chip on this board supports up to like 2 megabaud, which would be a lot better. But I think I need to update drivers to do that, and I just haven't bothered yet. I wanted to get it to work before doing that stuff. So anyway, you send... normally this transmission line, for example, there's a transmitter and a receiver, and the transmission line just stays high most of the time, and then when it's ready to send, it pulls it to logic low for one bit, and then sends out 8 bits. Might send out a parity bit. I'm actually not doing that because you don't need to. It depends on what your sender and receiver do and the particular chip that's on my board. You don't have to do that with. And then you just have a stop bit, which is just 1 for 1 bit of time, and that's it. That's all you have to do. So this will become important to us in a minute. And implementing that again was really simple. So I just made a basic transmitter that it can tell you whether or not it's ready to send stuff or otherwise whether it's busy. And then you can give it a write request with this data when you're ready to send stuff. And then there was basically just an interface between that and the memory mapper, which this one handles the 2 registers. So the memory map again is really basic for this. I just have a couple registers. This first one here, which is 2100 or 2100 100. This is the status, and so you can read this, and actually only bit 0 is used. Let me pull. Whoops, that was not helpful. I was trying to. That'll work. So this one is just the status, and only bit 0 will tell you whether or not that it's ready or not. So 1 means it's ready, so you basically sit there and you can wait on that. And then this one, as soon as you write any 8-bit value on that, it will start a transfer unless it's already busy. Then it just won't do anything. And that's just a really simple interface to implement. And then again, from the software side, you can see this is how we would use it, is we would just sit here and check the status register. And then check for that busy bit and wait while it's not ready. I should call it a ready bit because that's really what it is. So we wait until it's actually ready, and then we just send whatever byte we want to send, and that's it. That's pretty cool. Other than that, and fixing some really dumb errors. Let's see, what else did I do? Yeah, so one of the things I ran into today, and this made me furious. The initial way that I had these registers, is I would do something like this: static volatile uint 8t pointer xw leds is uint 8t pointer, and then the value. So I did this, and then you would use them exactly the same. This code down here doesn't change at all when you do that. What happened though, and this was really weird. I don't know if this is a bug or this is just not the way you're supposed to do this. But what happened is that with optimizations turned on, it turns out that I mentioned that small data pointer, or that small data section. It decided that these registers belonged in there, which is ridiculous because I gave them the specific address. So somehow it generated code where these symbols actually pointed to stuff in the small data section, which was not good. So I actually spent a while today trying to debug what I thought were totally my fault in the CPU implementation, only to realize when looking at the disassembly that those symbols had actually been placed in the wrong place. By the way, again, using an off-the-shelf CPU architecture for this was such a good choice because just the fact that I have stuff like, I can build everything in compile C, but I can also use obj dump to actually look at the different sections that are here and make sure that things are okay. In particular, I have like this symbol table, and this is actually how I found that it was doing that small data thing. Those symbols were actually put in here, and I could see where they were in memory, and I just saw that they were in the wrong place. In this case, they don't show up anymore because now that I've changed them to these defines, which seems to get around that issue, then they're not actual symbols anymore. These are just macros. So yeah, that gets pretty simple. And the code here is also really easy to read. I also have this dumping with this dash. Where is it here? I'm not seeing it. Here. I'm dumping this stuff from the elf file, which is sort of an intermediate when it's making the ROM. And I have this -m no aliases, which means like all those pseudo instructions and everything that were in the risc-v specification, this strips all those. So this will actually give me the exact instructions that it's running, which is a lot more helpful when you're implementing the CPU, for example, because you can see the exact instructions that are running rather than their aliases. So that's actually really helpful. Anyway, that's about it for what I've done so far, and I've totally lost track of the chat. Sorry about that. By the way, hi to guys in the chat: Freeful, Pyro ESP, Zakor, Wister Tove, Creekpot, Dark Second, Love Like Semtex, MS Visser, Danny Fritz. I don't think I missed anyone. Hope not. Yell at me if I missed you. Oh, that's cool, Miss Visser. Both that you're working on Pipeline Core and that you borrowed that linker script. I think as well in this one too, like I think it's missing a bunch of sections. Like I think GCC can actually output a ton of different sections, but I just did the ones that I've seen so far and the ones that I know where they're going to go. And if this causes problems, I don't really care. I'm not going to implement libc, and I'm not going to do, I'm only going to take this so far. So whatever works is the best thing. Freeful said, how much cache will you have? I'm actually not planning on having cache right now, mostly to simplify things. So right now, none. If I have any cache later, it's probably going to end up that I implement an instruction cache only. And then later I might also implement some fast RAM, but I wouldn't do that as cache. Pyro says, shouldn't the LED interface be I/O interface? Does that matter? I mean, as far as I'm concerned, like having it as register, I mean, I guess I could have it as like some other interface between there that would be like, here's the I/O interface, here's the system registers, but really they're kind of the same thing. So I just don't really, I don't know. I don't see a useful distinction there. Yeah. So that's where we're at. Couple things. Yeah, so what I wanted to work on today and why I called this fun with UART is, first of all, I really have spent a lot of time, like today especially and yesterday, just looking through those big dumps of stuff. And like, hold on. Yeah, so at some point there's going to have to be like some register somewhere that's going to be, this actually refers to the LEDs. And maybe that's, IO port 20 or whatever, but in my case it just made sense to expose that directly. So that's all it is. But yeah, so I've been spending a lot of time looking at these big trace dumps, and like they're not terrible really in terms of what you actually need to find. It's all in there. It gets to be a bit of an eyesore, but I actually feel like I'm getting faster at recognizing patterns in here anyway. So I actually want to stick with the crappiness of it for a little while longer, just to get better at reading these things. But I didn't want to do too much more of that today. at least not tracking down more of these CPU bugs, because it really is like, it's really boring. Like I'll put the thing on the FPGA and the LEDs won't light up, and then it's like, okay, what happens? Like, what happened? What did I get on the UART? Did I get half a string? Did I get something else? And then it's just kind of reducing until I can figure out where the problem is, and then, finding where things went wrong in the timing diagrams. And I'm just really sick of doing that this weekend. So what I decided that I wanted to work on is there's a couple things here. One of the reasons I did UART output is basically so that we could get some kind of printf here while we're setting everything up, particularly when we move on to set up the HDMI transmitter and everything. We're gonna have to do some register setting over I2C, and I've last time I did that, it was pretty finicky. So I would really like to expose that to the software as much as possible, so that we do as much of that there, and then we can also like print out register status from the HDMI transmitter. And be able to debug things progressively that way. So, I mean, we will still be, changing the hardware and iterating on that, but it should be a lot easier for us to see what's going on as we debug that, just because we have this simple output interface. So that's the first reason. The second reason is I'm thinking for that, and even a little bit more ahead, and also just to ease debugging for myself. I would really like a way to live reload code in this thing. So the only code that actually exists here is ROM. But what I'm thinking that we can do is just add in a separate hardware unit, because this UART goes both ways, right? So there's a transmitter and there's also a receiver. So I'm thinking that if we can send over new ROM, I could build in a little hardware unit that just whenever stuff comes in on that RX line, it just holds the processor in a reset state, and then just goes and replaces the ROM, because it's really just RAM with no write port right now. And I can just add the write port to something else and just not give the CPU access to that. Anyway, then it would just reset the CPU and hold it in that state and just replace the whole ROM, and then reset the CPU is what I'm thinking. And what would be really cool about that is that would allow us to, again, reload code live. And so especially like when doing the HDMI transmitter stuff, I think that'll be really useful. Really, when bootstrapping anything like that, it'll be useful to just swap out the code faster, because it's like 5-minute recompiles already, just recompiling the hardware. And especially as we move into things like building the rasterizer, I know I'm going to want to prototype that on the CPU. And after setting up a lot of the simulation stuff, it's feasible to do a lot of that stuff in a simulation environment, but it's not going to be real time by any means. So I'm thinking that having a way to reload the software on the FPGA in a really quick manner is going to be really valuable. Currently, that would only be at 9600 baud, which is really not good. But I feel like if I can get it working at that rate, then I can work on, making it faster. So we'll start with that. Anyway, I want to implement that really early, because the earlier we have that, the easier it's going to be to implement everything after that. And I feel like if I want to do that, after we have that, it's going to make things easier. And if I'm going to do that anyway, I might as well do that pretty early on. So I started with just the transmission to wrap my head around UART again. But of course, we're going to have to implement a receiver as well. Anyway, I think this will work out pretty well. And I don't know how far we'll get today. It's already been 45 minutes, and I've just been talking about what's been done on the project in the last week. So I have no idea how far we'll be able to get, but I did come up with a couple ways to do this sort of stepwise. Hey, Escatas. So what I want to do is, so we have this UART transmitter. What I want to do is first just do a loop back kind of thing, where if we start sending data on the UART, what I want the thing on the system to do is hold the CPU and reset and just route everything back to the transmitter. In fact, it probably doesn't even need to touch the CPU yet, but that's kind of what I'm thinking. And that way we can test this. Like, the thing that I'm worried about is receiving the UART. I'm worried that that's going to be finicky. I don't think it'll be that bad, actually, but I'm like, it's an unknown. And so what I want to do is I want to take advantage of the fact that now we have a working transmitter, so that we can use the transmitter to help test the receiver as we build that up. That's really what I'm thinking. I also don't want to expose an interface to the receiver to the actual CPU, just because I don't feel like that'll be particularly helpful. I think being able to replace the code and just doing a really simple solution for that is going to be a lot more valuable. So that's what I'm thinking. And yeah, before we start that, I'll bring over this UART thing again. So I did mention the protocol, and then sending that is really easy because you control the timing and everything. When you're receiving, it's a little bit harder because you have to watch for the stop condition, and then you want to read the values at sort of half bit intervals, or well, at full bit intervals, but like half a bit offset after the start bit. Now, if you want to make it really robust, you should really do things like when you see as soon as the transmission line goes low, then you should actually wait half a bit and then like check if it's still low to make sure that was like a real pulse and not just something spurious, and then sample out the 8 bits and whatnot. Also, I don't know what it's going to do in terms of sending parity bits and stuff, so that'll be kind of interesting. But yeah, I'm thinking, well, we'll have to see. I expect this to take some iteration, so we'll see what happens. Anyway, I'm probably going to make this as simple as possible and not terribly robust, because I expect that a lot of the things like between the COM port and the USB interface, I expect things to work. So I don't expect this to be that crazy. See you later, Dark Second. And at the same time, this is really only going to be used to reset the system and load new ROM. So like, I don't really want to implement like a very complicated protocol. I don't want to implement, like failure cases, because I can just send it again. I can just reset the FPGA. So it's like, it needs to be only as robust as it needs to be. So this should actually be a much smaller project than, for example, the thing we did with the Virtual Boy, where we had like multiple layers and all the different parts of the protocol had to accept a lot more failure cases. I think this is going to be a lot simpler, just because the actual thing that it does is it's only going to do unidirectional transfer. Yeah, this should actually just be a lot simpler. So let's start with doing that. I'm just going to get right into the RTL here, because I have a general idea of how this is going to work. Now this clock divider, I called it a UART transmitter clock divider. I think I'm just going to rename this to UART clock divider, because I'm also going to use the same clock divider for the receiver. I'm just going to run it at twice the rate. Not yet, Creekbot. Maybe eventually. Yeah, it probably did escape this. You'll be lacking a lot of context, but at least you'll see a lot of the action. Probably a decent trade-off. And I think the transmitter, our clock divider here. In fact, what I should do is I should actually put these in their own directory. And Sublime is crap with some of this, so we'll just do it this way. And we're going to have to do renaming and moving stuff like this is kind of annoying, so we'll have to deal with some stuff. It's also really crap that I just have this really long line in the make file, but again, who cares? So I'm just gonna run make test here just to make sure that I have everything, the right names and stuff. This is kind of like a quick build. I'm also gonna update the FPGA project right now, so we're gonna wait on kind of a long recompile here, but that's gonna be fine. One of the things with this kind of design flow is you get a higher tolerance for just moving windows around. I'm just removing these UART files from the project. I'm just going to re-add them. I don't know why this stuff is this slow, but it totally is. There we go. And now I'm just going to run this again. And I'm going to wait for it because I don't want to be changing files under its feet. Although I guess I can work on the receiver code. That'll be new anyway. Some of this stuff. Okay, a couple things. First of all, this is going to need an input. I'm just going to call Rx. And then it's not really going to have a ready signal because it's not going to have any, like, you're not going to tell the receiver to do stuff. So it's really just going to be something like output 7 down to 0 data and output data ready. And then we're going to want to register these. That's helpful. And I'm still doing this pattern because it actually works out pretty well, I think. Nope. I don't know what's happening with my typing again, but it's fine. Sweet. So this will just be the receiver. If we want to stick this, behind a FIFA or something, that should be handled separately to this interface. This really should just be hooked up to a reset and a clock. And then it should be able to output data whenever it gets stuff on the RX. So I think this is totally the right interface at this level. And this is 3 minutes and this is still going. You also get used to multitasking with this stuff. Yeah, so in terms of actually doing this, we need a couple things. We're going to want the clock. So I think the transmitter... I also had a reset on this clock. Yeah, I think I know how I'm going to do this. Wacko's God, I'm using a Max 10 FPGA development kit. That sounds super general. It seems that when I respond with that exact answer, that's actually the name of the kit. It's an Altera kit. So it sounds like I'm just saying, oh, I'm using a Max 10 board, but it's actually specifically Max 10 FPGA developer kit. Lokemind Mats, thanks for the follow. Man, what is up with my face alignment? There we go. Oh yeah, I forgot to mention that this was totally the camera I got for the Virtual Boy. That's just been moved here. I think it was Dark Second that actually asked that, and he's gone. But anyway. Now I think I don't actually want this to be baud clock. Because this won't be the baud clock, it'll actually be double. And I actually do want to prefix all these names. We can start with that. We're going to have a state machine in here as well. Just assuming it's going to be 2 bits. I think it will probably be more, but we'll see. By the way, completely unrelated. I made a point at playing a bunch of Gravity Rush 2 this weekend. That game rules. What do I call this in the transmitter? I just called it bit. That'll work. So this just mirrors the states that were in the transmitter, and maybe this makes sense. We'll see. So it's basically going to be this. If Rx goes low, then we want to do a couple things. We're going to reset the baud clock. I'm totally thinking the same thing, SK Thess. Like, this has been one of those projects that for me has felt really empowering. Like, there's a lot of technology that, like, I think it's pretty amazing that I can. In this case, this is a $200 board. It's a bit less now, but like, for example, this could be a $70 board. I think is what the ones from can't remember the brand, but whatever they go for, and with that board and like a computer, like I can sit in my room and design a chip. Like that's pretty cool. Like design a whole computer even. Like, and I have 2 laptops that I can do this on with as well. It's like I can sit down in a coffee shop and design a GPU. That's pretty crazy to me. Welcome to the future. So yeah, so we're basically gonna do the same thing. We're gonna reset that clock, and then I'm also just we're gonna go to the start bit state. And I think what we want to do here is we actually let's do it this way. We'll just assume that this is correct, and then we'll count out 3 clocks, and then we'll start moving to the data. I think that's sort of the easiest way to do this. So we can do something like this. Now we're only going to need to count up to 3 clocks at a time. So we can do this. Thanks, SK Tess. I hope so too. This has been really fun. Yeah, I'll stick this down here. So we can do this. We can call this tick counter. Yeah, stupid long name, but that doesn't really matter. We can reset that to 0 as well. Because then what we can do is we can... Let's see, how do I want to do this? Yeah, let's do this. So every time there's an edge on one of these... Or actually, we'll deal with that later, because it'll probably be easier to put that in line. We'll see. Set to 0 there. And so here, if the clock edge, so if we get an edge on this clock, we're going to just increase this counter. You know, I actually do want to do it like this. Whenever we get one of these edges here, I'm also super aware, by the way, that you don't need begin and end on all the statements here. It's just, I like to see it right now, at least. I don't consider myself a very, as you guys would probably guess from a lot of this stuff, a very experienced logic designer. So it helps me to see that and like write out the size of the literals and stuff. Just helps. Anyway, this way we can just always increment this whenever we have one of these clock edges, and then we don't have to transition on these edges. We can just do this. If this counter is 3, so here we reset the counter and we reset that clock itself, and so then we wait for it to count up 3 times, right? Because here it'll be 0, and then 1, 2, 3 will be halfway in this bit, and then we'll wait on 2 clocks during the bit stages, and then the stop bit will also do some waiting. Yeah. So if this gets to 3, then we just transition, actually. We also want another counter, though, which is which bit we're on. So, and that is going to need to count up to 7. So that needs to be 3 bits. What did I call this in the transmitter? I think I called it bit send index. You can call this bit receive index, just to match that, which I think is a good idea. And yeah, so we're going to transition there. We're also going to reset this counter, and I think I did exactly the same thing in the transmitter. Yeah, I just reset it here. So we'll do the same thing. So then we have state bit. And here, yeah, actually another thing we'll want to do is we'll want to reset this counter. because then we'll basically have the same thing. Only we'll check for 2 this time. And we're going to make sure we reset that. And we do if our bit receive index is 7, then we're actually done. We're going to stop its state. We'll always reset this. That actually makes sense to me. And I think that's it, actually, in that case. Otherwise, we're going to do a couple things. Like increment this counter for the next round. And actually pull in that bit. So in this case, I think we just do this. I think we can just do that. And then for our say stop bit, we're going to wait 2 more ticks. Which should put us here. Now that may put us into the parity bit. And we don't know if it's going to send parity or not. What I'm thinking is that we wait until we're definitely inside this last bit or inside the stop, and then we're just going to sit here and stay in that state. Or we just move into a state where we just wait until the transmission is over. So the way I want to do that is I'm actually going to add one more state here. And EOT, let's call that. Again, we don't know if the parity is going to be there, so I want to wait until we're at least in the parity or the stop bit. And then I just want to have a state where we just wait until Rx is 1. Then we're going to reset. And just to shut the compiler up, let's go to idle state otherwise. That looks good to me. Also, this finished a long time ago. I'm just going to run this, and this should work. I don't know if you guys caught that. When you'll do that, you'll see some programming lights over here blink a bunch. And then you probably can't see it, but the UART light back here blinks because it sends us these messages again, and then it restarts. So I'm actually just going to do that again so you guys can see that. And we're building, and we're blinking. So pretty cool. Yeah, so our rename was successful at least. And in the meantime, it seems like we've written something good. Now, I think we probably will have to implement some kind of protocol, because when I'm thinking about this, we need to tell the thing that the transmission ends. We don't want it to always send 64K every time, because that will actually take some time. In this case, it's going to be 9600 baud, which is about a kilobyte a second, and I don't want to wait a whole minute to reset the ROM and make sure this works. So I'd rather send it smaller transmissions. So what I'm thinking that I can do is have a very simple protocol for this. Let's actually just start setting up the higher level stuff here. I'm going to call this ROM loader. This net type thing. And we need the UART receiver inputs. What else do we need? For now, this is just going to be a loopback, so we need the transmitter stuff. And that should just be these signals. So I'm just calling it ROM loader so I don't have to rename it later, even though this is totally just going to be loopback now. So these, of course, are going to be outputs from our perspective here. And I'm just going to call these UART. Prefixing like this all over the place makes for long names, but it makes for very obvious code. And that's a trade-off that I'm pretty happy to make. Yep. Here again, well, we'll start with some of the obvious stuff. Okay, so basically, I'm thinking that we'll start in, we'll have a little state here. I think we'll have an idle state, of course, just deciding that there's 3 bits here, because we don't know yet. And so I think this will just wait until we get, like, I'm kind of imagining the protocol in my head, and I think all we're going to do is we can just start sending, we can send a length. It needs to be able to, it needs to be a 17-bit length at least. We could send 4 bytes because that's just the easiest thing to do. And then, so we can send a length and then that many bytes, and that's our entire protocol. I think that's the easiest thing we can do. So we're gonna have an idle state. We're gonna have a receive length state. We're gonna have a receive data state. I think that's it. So that's cool. Now, assuming the data rates are the same, this should just work. I'm thinking maybe we want to stick some of this behind FIFOs. But really, it should just kind of work out. I'm worried that the rates are going to be slightly different, so we probably are going to want to do that. It'll be different when we replace the ROM, though. So I might skip it for now, because we don't need the FIFOs when we replace the ROM, since the write to the ROM is going to be so quick. So I think I am just going to skip that for now. Yeah, I'm going to do that. So then we only have these 3 states. So that's pretty cool. We did that in 2 bits. So we need a couple things here as well. We need our length. And then we're going to need and receive index. That should work out for that. And then we need our, this can be up to our length. This will be our data receive index. It's probably all the state we need for this. So that's cool. Yeah, maybe I do want a FIFO here. We'll see. Start implementing it. I think we're gonna want that. Otherwise, we might miss data. Anyway, stay idle. So here we basically just wait until we actually get some data. Always getting bytes at a time, so if we're in the idle state and we get a byte, we're going to do a couple things. First of all, we know that this is actually the first byte in the length. You know, speaking of which, we actually only need 2 states. Because we're either receiving the length or we're receiving the data. This is all we need. Cool. So if we get data ready, we're going to do a couple things. If our length receive index, or first, actually, we're going to do this. We're going to do our length next, and this, yeah, this will probably be fine. How do I want to index this? Well, so I want, for example, 7 down to 0. We're going to do this. Something like this. Actually, this is the easiest way to do this. Is we do we'll do this. We'll shift it in the top. And len next 31 down to 8. Yeah, that'll do it, because that'll shift it down. And then we can do data. So this should happen on 0, 1, 2, and 3. If data receive, or length receive index is equal to 3, then we're going to transition to the next state. Otherwise, we're just going to increment it. State receive data, and then we don't need to latch the length. This is going to change. That's the only time it's going to change. And then we do want to reset this, though. Let's see the receive index. And then otherwise, we're receiving data. And so all we need to do here is we wait until data is ready. That's easy enough. Going to output the data to our FIFO or whatever our output thing's going to be. And then we have to do this. I'm actually going to do this. Our data receive index next is data receive index plus 1. And you can totally just tap on the next value here. So if the next value is going to be our length, then we're done. Then our state is going to be receive length, and we can do our length receive index is going to be 0. I like how simple some of this stuff becomes. Yeah, this actually can stay the same because we can put the FIFO after this, so that's actually nice. Then we need 2 more things. We need the thing that pulls off the stuff for the loopback, and then we need the FIFO itself. So I think the only new hardware unit we have to make is this one. UART loopback output. I'm just putting in the top level stuff because, again, this is just some test crap anyway. And yeah, we're actually not going to care about the ready signal here. Because it just keeps us in these 2 states. Otherwise, we would have to transition into a 3rd state, which would wait until it was ready and then do that. And right now, this will be fine. So then this becomes really nice, how simple this is. This will just be a couple things here. So first of all, you are transmitter write data next. So normally, well, that's actually fine. It's actually the write request is the only one we really want to say is 0. Because then here on the next cycle, we're going to write that data. And the write data is going to be our receive data. So yeah, so on the cycle following this, this will just push it out to whatever this interface is. And we're going to hook it up to a FIFO, and then another unit is going to pull off the other end of the FIFO that's going to actually loop back to our transmitter. That's all that is. So that. We don't even need to, really just need enough for the FIFO here. So whether or not the FIFO is empty, because we're just going to pull stuff off of it while it's not empty. So easy. Here we actually do want ready here. Yeah, of course it needs the data, and then we're going to do an output FIFO read request. I think read enable I called it. Yeah, this is going to be really nice when this fits together. Stuff comes together really fast for me now. At least when it's simple. I don't know why I'm answering Slack messages on stream. That's not a good habit. I should not do that. So this becomes really simple, I think, because it's basically if the FIFO is not empty and the transmitter is ready, then we're going to go ahead and read from the FIFO, write to the output, and the data is the way I have this FIFO set up. When you tell it to read enable, that really increments the read pointer on the next cycle, and whatever's on the FIFO read data already is going to be the data that you wanted to read out. So, this is it. I think this is the whole logic for that. And then if I just hook it up right, it just works. That'd be neat. Okay, so I'm just gonna hook this up probably at the top level of the Xenowing stuff. Maybe. Yeah, probably here, because this is where we have access to the UART transmitter. We're going to have access to the CPU stuff here later as well, so we're going to hook up some of that. But first of all, write data next? Oh, did I mess that up? Yes, thanks for the heads up. That's one of the things that actually I'm impressed at the compiler. Well, I mean, I'm not used to getting a lot of help from these Verilog compilers, but that's actually one of the things that it does do a good job at yelling at me at. or yelling at me for. Although it's so much faster when you guys yell at me instead, because don't even have to compile. All right, so I'm gonna pull this down on my other screen just so that I can read this simple while hooking this up. This is where it gets really boring. Because we just have to instantiate stuff. So we're going to have a ROM loader. I think System Verilog has something, is it interfaces or something? I can't remember what it was called. But you can sort of define whole blocks, and I think a lot of this instantiation code could be made simpler with something like that, but I need to look into that at a different time. For now, I'll just keep going. So the ROM loader needed a UART receiver data. And I'm just going to call that UART receiver data because we're going to instantiate the UART receiver in a minute. UART receiver data ready. We need the transmitter write data. And for this, we'll actually do FIFO write data. We're going to hook up the FIFO there. And this is going to be write request. And this is going to be the loopback FIFO write enable. That's it for the ROM loader. And then here we're going to do the UART loopback FIFO. Or actually, it's going to be a FIFO. Now, I think... yeah, we have to set up our parameters first before we do that. This looks like that. Yeah. So our data width is going to be 8 bits, and our depth, it's depth bits, so this will be 16 things, so that should be more than enough slack here. And so what does the FIFO need? Go ahead and hook that up. This needs, of course, the reset in the clock. We're going to fan out a couple signals here, not all of them. We need empty, for example. So empty goes to that. And then we need the write data and write enable, all that stuff. So write data and the write request. This, of course, is going to be 7 down to 0. Oops, and these aren't requests here. They're enable. Hey, Okama. I hope you're getting stoked for revision. Because I am as well. Especially since it looks like I'll have a lot of free time on my hands compared to previous years. So that should be it in terms of fanning out these FIFO signals. And then, yeah, these should be already hooked up to those right signals, which is great. And then the last thing we want to do here is a couple things. We want to make our UART loopback output. And a bunch of our usual suspects here. Yeah, that'll be awesome, Alkama. Be a really fun party. So we also need FIFO empty, and that's going to be this signal. FIFO read data. FIFO read enable. And the way that we're going to do the transmitter stuff, we need to actually fan out some signals from here. Now, not all of them, because I think, but the write request and the write data, we are going to want to fan out here. So I'm going to do logic, here, loopbook, this one, write data. Look at that name. And that's fine. Because we're going to need to do some combinational logic with this and a couple of the other ones. Particularly the signals from the CPU. So we want to pull these out into their own nets. And then this would be the ready, though, we can just route here. Because the UART transmitter ready signal should already be pulled out here. So then the write requests and the write data, I think I have them just being driven here by this transmitter interface. And what I'm going to do instead of that is fan out these here. We have the UART transmitter interface, UART write data. It's going to drive that instead. I guess I smashed all these together above, so I'll do the same thing down here. And so then we're going to kind of reverse this. So instead of fanning these out here, we're going to drive them with these signals. And we're going to do a little bit of arbitration here, because now we have two drivers that we actually need to satisfy here. And this will actually be easy. We'll just do this. Just do this as a ternary. And this is not a great way to hook this together, but it's fine. So it's either going to be, if the UART is sending a write request, we're going to use the UART one. Otherwise, we're going to use the loopback. And then we can just do the or of the two for whether or not we actually need a write request. This means that if they both try to assert a write request, we're totally going to miss out on the, with the way that this is prioritized, we're going to miss out on the UART from the CPU, and that's fine. I don't expect to use these at the same time just for these simple loopback tests anyway. But I think that's it. I think that's all we really need to do to hook this up, at least in terms of wiring everything together. We're going to need to add these things to like all the make files and stuff, so that's going to be kind of annoying, but not too bad. Transmitter interface, and we'll just add them here. UART receiver. We have our little interface and our FIFO. And we're going to do ROM loader and our UART loopback output. Multiple top-level modules. I don't know how that happened. Really, with how I declared these, I can't be. I know this command like this fine too. I mean, we can also do this. Just specify it directly. Does that work? All right, so a couple things. In Xenowing SV, we have UART transmitter ready, UART receiver ready, or data UART receiver data ready. Signal definition not found. Did I not make the receiver? I totally didn't, and that's probably why I thought that was a top-level module, actually. Let's remove this, just because I don't want it there if we don't need it there. Did I really do that wrong like that? Yeah, because I probably wanted to hook up the FIFO before that. That's probably what happened. Anyway, this becomes trivial because it's just UART receiver 0. Admittedly, hooking everything up here is really kind of verbose and painful. But that's what you get when you have to apply names for all these signals like this. Hey, Michael McMillan. Let's do that. And then there really wasn't much here. Also, we need to fan this out. That's really easy to do on the top level thing. Then yeah, we just need data. Oops. that. And in ROM loader, we didn't have a state idle, which is true because I reduced it to just state length here. All right, what else did we miss? Signal definition not found. UART transmitter ready. Did I not put that together that way? Oh yeah, I removed the wrong signals here. Well, it built. For better or for worse. All right. Let's just try this on the hardware. I really need to add a bunch of this stuff to the simulator. I haven't done any of the UART stuff in simulation yet. That will probably bite me in the ass later. So I'm going to just add ROM loader, loopback output. And then we also need to go in and add the UART receiver. So that we'll start with that. And then we need to do another thing here. I got to pull up my development kit user's guide. Oh. I don't know why my Adobe Reader isn't showing up in that menu, but I have it here. Because we need to know, and luckily the last one I did here was the UART TX, so we need to know which pin UART RX is, so it's Y19. So we're going to go into our pin planner, and the signal hasn't showed up on the left yet, so I'm actually going to run a analysis and synthesis step first. That's going to take a minute. Now, if we deploy this back on the hardware and everything goes okay, it'll just look like it'll operate the same way. And then I'm going to write a quick Rust program to actually try this. Again, it's just going to be loopback for now. Actually, replacing the ROM is going to be the next step. But as you can see, like it's not much different. Like the same thing here that's pulling off this FIFO and doing the loopback could just as well overwrite the ROM. And in fact, I probably won't even use a FIFO for that because it'll be so simple. And it'll be basically instant. So yeah. I think I'll do it whenever the UART receiver or the ROM loader, whenever it's in its, receive data state, it'll soft hold the CPU and the rest of the system in reset, and then just incrementally update all the bytes. It should be really basic how that works. Anyway, now that this is done, we should have our UART RX somewhere in this list not assigned anything. I don't know why we don't. Let's just do it this way. UART RX. Just do it manually. That's going to be... That's annoying that it says that. But this is a pin Y19, right? Yeah. And we want this to be 3.3 volts. And I use LVTTL on the other one, so it seems smart to use the same thing here. Let's just try it. See what happens. While this is compiling, I can start on the Rust program. I'm gonna steal some stuff from the Virtual Boy stuff because I can. Add fuzzy in here. And I used a serial port library, which looks like it was just called serial port. Dev projects, XenoWing. We'll put it in MISC. Cargo new bin. We can call this ROM loader. Yep. And so we'll add this dependency. I'm just going to go back into this fuzzer stuff. Steal some code here. From me. From past me. Who was so last year. Oh, did I crickpot? That's not going to be good. It's probably going to be fine, but you're right, I did. I'm going to stop that. Nice catch. And then we'll... Yeah, 3.3 AV LETTL. Now we'll do it. All right. Got a lot of little projects in here within this main project now, so. In fact, I'm actually going to do something here. I'm going to pull in that fuzzy folder into my other window here. That should help. Okay, so now I think all the actual interesting code was in other parts. Yeah, so we should be able to just do this. And we'll do this. And I think I can just do com5 here. I'll probably have to shut down putty for this. And we're going to want to set rates and stuff as well. Find that documentation here. Things may have changed since I used this library last. I think I'm actually just looking at a different library. come on. Where is it? Oh yeah, it's this one. Let's do expect here. Good enough for just like throwing this together. By the way, I think no, that's still going. And then just gonna copy some more code here. That and that go away. We're gonna do this. I think we do port up right. What do I do here? Like that. This will look real happy if it works. Can I do that? I think. What? Time duration? I think it is. That's what I thought. So we just do that. Probably do that on this one too. Yeah, we don't actually have the error here. Screw it. I'm being really lazy here, but this is going to be fine. Yeah, we don't just want to write all, though. Also being lazy here. I can fix this up later. Actually, I don't need these masks then either. So first thing I'm going to do is port right all length bytes. Then we can do, actually, we'll just do it this way. Like that. And then being lazy and I'm correcting typos. Start with that. I'm hoping I can just compare these like as slices. I wonder if I do that, if the asref coercion can just magic that away for me. Doesn't look like it. That looks good. So this finished. I am actually going to open up Putty really quick because I want to see if this works just like it did before. And that's COM5. Also, I think the name of that port might be crap. I actually should, before I just run this, I should, or before I forget that is, I think, okay, no, never mind. COM5 should be fine there. Yeah. Putty, and we'll run this. Looks like we're good. Now I need to close Putty because that's going to hold that COM port, otherwise we can't open it. And I should just try this. Cargo run. Worst thing can happen is it doesn't work. And then we got to debug it. But it's already like 10:15. So I think either way, I'm probably going to go after testing this. Oh, the read timed out. That could be for numerous reasons. I'm actually going to do this. Just in case. It might be that it's just not sending it back, but that's probably the case now that it's not coming back. So that tells me it probably doesn't work. Now, there's several reasons why. It could be that we're not reading it properly. It could be that things are wrong with this protocol. There could be so many reasons why this doesn't work properly. However, again, because of what time it is, I'm probably not going to look into that now. but at least you can kind of see how the pieces are meant to fit together. And this is kind of at least a good starting point, at least for building this reload. When this works, it'll be really sick. But until then, I'm going to head out. Thanks, guys, for hanging out, and I'll see you next time.